Alright, welcome to the next portion on graph sketching. So far we talked about restriction, right? Where your graph can exist, where your graph cannot exist. We also talk about your intercepts, so your x-intercept, your y-intercepts. And then we also talk about your stationary points, right? Stationary points. Now we're going to be talking about asymptotes. So actually, when you cover these four features, any curve, you basically can sketch any curve already. Almost any curve, right? You can basically almost sketch any curve already. So I will now show you what asymptotes are and how to find each kind of asymptote. Okay, so an asymptote is basically, you can just remember it as a line that my curve will never touch. Okay, a line that my curve will never touch. So for instance, in the earlier example that I gave you, right, remember the reciprocal graph that I drew, and then you realize that no matter how I stretch the graph, it will never touch the blue color line, right? So this blue color line over here is what we call our asymptote, okay? And asymptotes, there are three main categories for this. There is a vertical asymptote, there is a horizontal asymptote, and there is this thing called an oblique asymptote. Three kinds. One, two, three. So a vertical asymptote is one where it looks like that. A horizontal asymptote is one where it looks like that, where my graph will never ever touch it. So for example, like that, it never touches. This one will be, let's say, for example, like that, right? It never touches. And then a oblique asymptote is a line that has gradient. So it's a line with gradient. So it looks like that. And then my graph will never touch the line. Okay, so there are three different kinds of asymptotes over here, right? And I will use these examples over here to show you what is each asymptote. Okay, so we're going to be first talking about vertical asymptotes. Then after that, we are going to be talking about horizontal asymptotes. And then last but not least, we are going to be talking about oblique asymptotes in the practice questions below, right? So far, at this point, you just need to know there are these three different kinds of asymptotes. And the whole point of this practice is based off the equation of a curve, right? So for example, y equals to x minus 1, x minus 3, right? How to find the equation of the asymptotes. Because remember, these asymptotes, at the end of the day, right, they are all just straight lines. So since they are straight lines, they all also have their own equations. For example, the vertical asymptote over here will be x equals to something. Your horizontal asymptote will be y equals to something. And then your oblique asymptote will be y equals to mx plus c, right? Because at the end of the day, they are all just straight lines. So our job over here is to find out the equation of these asymptotes, the three different kinds of asymptotes given the original equation of the curve. Okay, so that will be all for this fundamental concept, even though I have not taught you how to find it yet, but at least now you know fundamentally what asymptotes are and the three different kinds of asymptotes. So in the practice questions below, we will actually go through how to find them in specific, and I'll use each of the question. So I'll use part A of each question to teach you the concept, and then B, C, D, I will leave it up to you to go and solve it, and then I'll go through the answer together with you. Okay, if not, I'll see you in the next video. Alright, so let's go through the first type of asymptote, which is the vertical asymptote. I'm going to be explaining the idea behind it, then we will go into exactly how to solve it quickly in the exam situation. So a vertical asymptote is one that shoots upwards, right? And it has a general equation of x equals to something. So the whole idea of a vertical asymptote is that, let's say I call this A, okay? And then let's say my graph looks like that, and then it looks like that, right? So the whole idea behind a vertical asymptote is that as the x values on the x-axis approaches A, right? In this case, A is here, right? As the x values all approaches A over here, the y value at A should approach plus minus infinity. That's the whole idea behind it. So if we use 1A as an example over here, right, for A, y equals to 1 over x minus 1. When will the only scenario that y can approach plus minus infinity, right, for y to approach plus minus infinity, the only way that this is possible is when I take something divided by 0. So it's usually when I have something divided by 0. The something is here. So if you look at this equation over here, the only possible case for this y value to approach plus minus infinity is for the denominator over here to be 0. So for y to approach plus minus infinity, y must be 1 divided by 0, because it's only when you divide anything by 0 then it approaches infinity. So if we do a direct comparison with these two, we see that for this to happen, x minus 1 must be 0, right? So if x minus 1 is 0, we solve that x equals to 1. So therefore, when x equals to 1, y approaches plus minus infinity, right? When x equals to 1, y approaches plus minus infinity. And that is how we derive that x equals to 1 is the vertical asymptote. So in other words, how we find the vertical asymptote is very simple. You just need to let the denominator be 0, and then you solve for the x values that give rise to that. It's as simple as that. So yeah, that's basically the answer right over here. So same thing for B, C, and D. The whole idea is the same thing, right? You can feel free to pause this video now to actually attempt the questions over here. But I am just going to show you the GC plot for B, C, and D. Okay, so for B over here, right, the whole idea is very simple. Again, I'm just going to scroll down. Maybe I zoom out a bit. Right, for B, y equals to x over x minus 2, x plus 3. So from here, we can tell that for y to approach plus minus infinity, x minus 2, x plus 3 must be 0, because the denominator must be 0 in order for infinity to happen. So we get that x minus 2 is 0, or x plus 3 is 0, and therefore x equals to 2 or x equals to 93, right? As simple as that. So if I were to sketch the graph for you to see on the GC, if I do this and then I enter, and then here I key in the same thing, x over x minus 2, x minus 2, and then x plus 3, you see that there are asymptotes, right? The first one is here at x equals to negative 3, and then the second one is at over here when x equals to 2, right? As simple as that. So that is basically the approach to that, right? So for part C, same thing. For C, for y to approach plus minus infinity, right? We know that x squared plus 5 must be 0. But then you look at this over here, there's no real solution to this, right? Because you see that for the discriminant of this quadratic equation is b squared minus 4ac, right? There's no b, so it's 0 squared minus 4ac. I get negative 20, which is lesser than 0, right? And since the discriminant is lesser than 0, that means that this equation over here has no real roots. No real roots. And since there's no real roots, it tells me that there is no x value that gives me y approaches plus minus infinity. So basically, there's no x value. And that's why over here, you see that there is no vertical asymptote. Okay, for part D, is slightly more interesting. It's slightly different because it's not your algebraic expression. But this is y equals to ln here. So for logarithmic graphs, you just need to remember that this inside here, okay, this value over here, it can never equals to 0. Okay, so it can never be 0. And why is that the case? Because remember, ln at the core of it is log base e equals to something. Now, e to the power of anything will never become 0, right? It can be 1, but it can never be 0. You cannot raise anything to the power of something, and then the answer come out is nothing. So for this case over here, we know that when 2x plus 3 is 0, then y will be undefined. In other words, y will approach plus minus infinity, right? Because it will not exist. So what's the value of x in this case? When we solve for x, we get that x is negative 3 over 2. And that's the final answer to this question over here. Okay, so that is it for vertical asymptotes. I hope that I have provided a clear explanation of what it is. And let's start horizontal asymptotes. We talk about vertical asymptotes. Now we're going to be talking about horizontal asymptotes. So again, a horizontal asymptote is one that looks like that, whereby it's a flat line that my graph, no matter what, will never touch, right? So the whole idea behind this concept is this. And the general formula for this is y equals to something, right? And I'm just going to call this b over here. So the whole idea behind it is, as my x values approaches plus minus infinity. So as my x value over here, as it goes back and forth, right, plus minus infinity, my y value will approach b. Because as I stretch this line out, towards infinity, you see that my y value over here, it will go very, very near to the line, but it will never touch it. So the whole idea behind it is, as my x becomes very, very big or very, very small, my y value will approach the b value. So how do we exactly find horizontal asymptotes given an equation? So I give you an example over here for A. Y equals to x minus 1 2x minus 3. Now, the tip from me over here is to always, for algebraic equations, for algebraic expressions, is to always reduce your fraction to a proper fraction first. So we can see that this fraction over here is improper to begin with, because the degree here is 1 and then the degree here is 1. So we need to reduce it to a proper fraction first in order to be able to clearly tell what's the horizontal asymptote. So a way you can do this is very simply, it's just do long division. So I have x minus 1, 2x minus 3, divide here I get half, minus 2x minus 3, minus 2x, then minus 3.5, and then in the end here I get half, right? So in the end, this one will be reduced to half plus half bracket 2x minus 3. Okay, so far what we have is this, and then I can expand this to get 4x minus 6. Okay, so this is equivalent to this, they are the same thing. So now, by doing it this way, and now that this over here is a proper fraction, it becomes so beautiful to find out what's the horizontal asymptote, because as x approaches plus minus infinity, right, you can see that as x approaches very, very big or very, very small, you realize that this denominator over here becomes infinity, right? It approaches infinity as well. 4x minus 6 approaches plus minus infinity as well, right? Because when x becomes very, very big, you sub a super huge value of x inside 4x minus 6. 4x minus 6 will also become very, very big, right? And when 4x minus 6 become very, very big, given that 4x minus 6 is in the denominator, 1 over 4x minus 6 actually approaches 0. Because when the denominator is very, very huge, the whole fraction becomes very, very small. And I'm not saying that it becomes 0, I'm saying that it approaches 0. That's why we have the arrow over there, right? And when this fraction approaches 0, the overall y value will approach half plus 0, which is the same thing as y approaching half, right? Because you see that this half value over here is independent of x. So since it's independent of x, the x value, even if it approaches plus minus infinity, it will not affect this y value over here, right? And therefore, the horizontal asymptote is simply y equals to half. And that's the final answer to this part over here, right? So yeah, that is basically it for part A. The whole idea is always reduce your fraction to a proper fraction first. Once it's in a proper fraction, then you ask yourself, as the x value tends towards plus minus infinity, overall, what happens to the value of the whole entire equation, right? What value does it tend towards? And the value that it tends towards will be the horizontal asymptote. Okay, so feel free to pause this video now to go and tackle the rest of the other questions before I actually run through the questions with you. Okay, if not, now let's go through the rest of the questions right now. So I'm just going to answer part B over here. Y equals to x over x minus 2, x plus 3. So you realize that the degree here is 1, the degree here is 2, right? Because we have a quadratic below. And therefore, to begin with, it's already proper. So you can straight away just observe the behavior, right? As x approaches plus minus infinity, given that the denominator is larger than the numerator, right? If I have a linear on top and a quadratic below, and as my x value increases towards infinity or decreases towards negative infinity, you realize that the denominator, it increases much, much faster than the numerator, right? Because below is quadratic, but then the numerator is just x. So since the bottom increases at a quadratic rate and then the top increases as a linear rate, the bottom will increase much faster. And since the bottom increases much, much faster, therefore, we know that overall, when x approaches plus minus infinity, my y value will actually approach 0, right? Because when the bottom is huge and then the top is small, the whole thing actually approaches 0. So therefore, the horizontal asymptote is y equals to 0 as the final answer over here. Okay, so that is for B. Now for C, I'm just going to answer the C over here. Y equals to x squared over x squared plus 5. Now, first thing, degree is 2. Degree is 2. I need to do long division to be able to get a proper fraction. So x squared plus 5, divide, I get this, right? Negative 5. So this can be written as 1 minus 5 over x squared plus 5. And then you see that now I have a proper fraction over here because the top, the degree is 0, the bottom, the degree is 2. So here you can observe the behavior. So as x approaches plus minus infinity, x squared plus 5 will also approach plus minus infinity. And therefore, negative 5 over x squared plus 5 will approach 0 because small over very, very big. And overall, y will approach 1 minus 0, which is y will approach 1. So therefore, y equals to 1. is the horizontal asymptote equation. Okay, now lastly we have D, y equals to ex plus 3. Now for this one, you just need to, for exponential equation, you cannot use the same method because it's not an algebraic expression. But for a exponential equation, right, if you draw the graph for this, if you recall, or if you look at your GC, you get the graph that looks like that, right? And then here, this line here is y equals to 3. So for an exponential graph, you don't even need to do any working. You can visually observe that it's just y equals to 3 as the horizontal asymptote. Yeah. So that's the whole answer to question BCD. And with that, we conclude the concept of horizontal asymptote. Next, we'll go through oblique asymptote. Any questions, let me know in the comments. If not, we're going to be discussing this concept in detail right now. And recap what's an oblique asymptote. It's just an asymptote with gradient. So y equals to mx plus c. This over here is the oblique asymptote. So how do we find out what's the oblique asymptote? The concept is very, very similar to the previous portion. You need to first make the fraction into a proper fraction. So over here, we can see that this is improper. You can see that this is improper. So to find out the equation of an oblique asymptote, we first make it into a proper fraction. So for part A, y equals to x squared over x minus 1. What we're going to do now is to do long division first. X squared, x minus 1, x squared minus x. So in the end, over here, we get x plus x over x minus 1. Apologies, can still reduce. So plus 1 minus x minus 1, 1. So in the end here, we get x plus 1 plus 1 over x minus 1, right? This portion is here, and then here is here, and then it's still being divided by this, right? So that's what we get. Now, same concept as before. As x approaches plus minus infinity, right? As this x value approaches plus minus infinity, as we drag out this line even more, you see that this curve, it will never touch the line because it's basically the asymptote. So as x approaches plus minus infinity, we know that 1 over x minus 1 will actually approach 0, right? And overall, the y value will approach x plus 1 plus 0. And overall, the y value will approach x plus 1. So therefore, y equals to x plus 1 is the oblique asymptote. Because if I were to drag this whole thing out, right, and I extend this line even more, you see that the y value, it eventually tends towards x plus 1, and therefore x plus 1 is the oblique asymptote. As simple as that. Okay, so that's the concept behind it. Very, very similar to the previous one. So feel free to pause this video now to tackle part B, and if not, I will jump right into part B. Okay, for part B, y equals to x squared plus x minus 1, x plus 3. So same thing, you do your long division first because the degree here is 2 and then the degree here is 1, right? So we need to do long division first. So we take this x squared plus x minus 1, x plus 3, x minus x squared plus 3x minus 2x minus 1 minus 2 minus 2x minus 6. We end up with 5. So this whole thing here can be reduced to x minus 2 plus 5 over x plus 3. So the same idea behind this as before. As x approaches plus minus infinity, right? We know that this whole fraction here will approach 0. And therefore, the y value will approach x minus 2. And therefore, y equals to x minus 2 is the oblique asymptote equation. Right? And with that said, we have come to the end of all the 4 features you need to include when drawing a graph, and we conclude the first portion, which is the basics of graph sketching. Okay, so any questions, let me know in the comments. If not, I'll see you in the next video.